Absolute value equations can be fairly straightforward, but occasionally a little bit tricky, and we're going to see how to solve them algebraically, but it's actually really important to think about what they look like graphically so that you can understand why certain things happen and why you're going to run into difficulties occasionally. So let's start off with linear equation. So in other words, you can think of the left-hand side as an absolute value function where the input is a linear function, so absolute value x minus 1, and the right-hand side also as a linear equation, x plus 3. Now, I'm going to do it algebraically first. You have to remember how to turn the absolute value equation into a piecewise linear function, and the first step there is to find the critical values. So the critical values, there's only one in this case, you set the argument, the thing that's inside the absolute value bars, equal to 0. So 2x minus 1 equals 0. That it becomes 2x equal to 1, x equal to a half. And so again, the point of the critical value is that when x is equal to a half, the expression 2x minus 1 is equal to 0. And you can think of 0 as the dividing line between positive and negative. When you take the absolute value of a positive, which is going to occur when x is greater than a half, you don't have to do anything. You just remove the absolute value bars. When you take the absolute value of a negative, you have to change the sign, which means putting a negative sign in front of it, and that's going to occur when x is less than a half. So in fact, that's how we're going to do it, and one way to sort of break up the piecewise linear notation is to use cases. So we can think of the case, the first case, as the case when x is less than a half. And if you recall the discussion from last time, I said that whether you write less than or equal to, it doesn't really matter, but we don't want to lose out on a root here, so it's actually probably a good idea just to put less than or equal to or greater than or equal to for all of these cases. So if x is less than or equal to a half, the expression inside the absolute value bars is going to be negative, which means that we will change the sign on it when we take away the absolute value bars. And that's now a pretty straightforward equation to solve. So we get minus 2x plus 1 equal to x plus 3. I can add 2x to both sides. And then I can subtract 3 from both sides. And then I can divide both sides by 3, and I get x equal to negative 2/3. And it's worthwhile checking. It's an equation, so you can check this. If you plug in negative 2/3, you get negative 4/3 minus 1, which becomes negative 7/3. The absolute value of that is positive 7/3. And then when you replace on the right-hand side x with negative 2/3, you get negative 2/3 plus 3, which is 7/3. So that is a root of the equation. Let's see what case 2 looks like. So case 2 is all values of x greater than or equal to a half. And in that case, the expression 2x minus 1 is positive, or 0, in which case, when we take away the absolute value bars, we don't need to do anything. We can just write 2x minus 1 is equal to x plus 3. And this is a particularly easy equation to solve. We can subtract x from both sides and add 1 to both sides. And easy enough to check that as well. If you plug in 4, you get 8 minus 1 on the left, and 4 plus 3 on the right, both equal to 7. And so we have two separate solutions. So the solutions are x could be negative 2/3, or x could be 4. Now, what's going on graphically here? Why do we get two different solutions? Because in the past, obviously, when we've done a linear, if you think of the left-hand side as a line, the right-hand side as a line, there's only one point of intersection. So why are we getting two here? So let's see what's going on in Desmos. We want to graph on the left. We have y equals the absolute, so ABS, absolute value of 2x minus 1. And it's got that V shape, and you can see the point of the V is right at a half. It's hard to get it right there, but okay, there we go. Point of the V was right at a half. And so the left-hand side is one line using piecewise notation. The right-hand side is one line using piecewise notation. Let's see, the right-hand side is just the line y equals x plus 3. And now it's pretty clear why we get two solutions here, because we have one point of intersection right there, and that corresponds to what we solved for algebraically. The x value is negative 2/3, negative 0.6666, etc. And when we plugged it in, we got a y value. In other words, the left-hand side and the right-hand side both became 7/3, which is 2 1/3, 2.33. The second point of intersection up here is 4, 7. And again, when we plugged in the, we got the x value of 4. When we plugged it into both sides became 7. And so there are the 2 points of intersection. And graphically, let's just do a sketch here. The absolute value function is that V shape. And the part on the right from the x value of a half to the right is just the function y equals 2x minus 1, which is this. So in case 2, we're just finding the intersection of the line y equals 2x minus 1 and the line x plus 3. The left-hand side is the line y equals negative 2x plus 1, and that's this line right here. So in both cases, we're just finding the intersection of a line, and we've just broken it into two problems because the absolute value function we can break into two lines. And the line x plus 3 sort of crosses above here and goes like that. So that's where you get your two intersections. Now, let's take a look at another one, this time a quadratic. So let's say we have the absolute value of x squared minus 2x minus 15 equal to x plus 3. All right, again, we've got to find the critical values. Critical values are going to occur when the expression inside the absolute value bars, x squared minus 2x minus 15 is equal to 0. That factors x minus 5, x plus 3, which means that x is either equal to 5 or negative 3. Now, here it's really going to help to have a sketch, because when you do the sketch, it's going to help you keep track of where the function's negative, where the function's positive. So those critical values are zeros, which means that the parabola crosses through the x-axis at negative 3 and 5. So when you take the absolute value of it, remember, everything below the x-axis is going to get reflected up. And by reflecting it, we're just putting a negative sign in front of it. So we can do the case 1, case 2 again. Case 1 is the values of x that make the expression negative, which are the values between negative 3 and 5. So from negative 3 all the way to 5. And if that's the x values we're dealing with, then when we take away the absolute value bars, we have to put a negative sign in front of the expression. So we have negative x squared minus 2x minus 15 equal to x plus 3. And let's expand this. Changes the signs. This is a straightforward quadratic. We can get everything onto the right-hand side by adding x squared. We'll subtract 2x, and then we'll subtract 15. and this factors as x minus 4, x plus 3, which means that x is equal to 4 or negative 3. So what's the line x plus 3 doing here? Where does that pass through this? Well, it passes through like that, and it has a 0 at negative 3. It passes through the x-axis at negative 3. The other point over here is at 4, 7. So when you plug in an x value of 4, both the left-hand side and the right-hand side become 7. And then obviously you have negative 3, 0. And if you're just looking at this graph, you can now see that we would expect one more point of intersection, and that's going to occur somewhere to the right of 5. So let's do case 2. Case 2 is when x is either less than negative 3 or greater than 5. And if that's true about x, then the expression x squared minus 2x minus 15 is positive, which means we can just take away the absolute value bars and don't have to do anything. And again, we get a straightforward quadratic. We'll subtract x from both sides, subtract 3 from both sides. This also factors quite nicely, x minus 6, x plus 3. And so x is equal to either 6 or negative 3. So we've got the negative 3 again, because that point there, if you like, belongs to both of the pieces. The piece that we left alone, the original parabola, and the piece that got reflected. And then you can see this other point of intersection that we were expecting is at 6. And then you can plug it into either one of the equations to verify that the y coordinate is 9. And so we end up with 3 solutions here, 3 different x values. X could be negative 3 or 4 or 6. These are all solutions to the equation. Now, on the right, I've given y values, but when you're solving an equation, you're just looking for x values. However, when you're looking at it graphically, it's important to realize that these are points of intersection. And so you can plug in the x values to figure out what the corresponding y values are. And that shows up if you were to plug in the points into the equation. The left-hand side is the y value, the right-hand side is the y value. They should be the same. Now, not everything is quite so straightforward. There are some problems that are going to arise. Let's take a look at one such problem. We'll go back to a linear equation. So absolute value of x plus 1 is equal to 2x. So the critical value occurs when x plus 1 is 0, which means x equal to negative 1. So we can have a case 1 when x is less than or equal to negative 1. If that's true, we take away the absolute value bars. We have to change the sign of the expression. I'll expand this, minus 2x minus 1. I can add x to both sides, and then divide both sides by 3. And we get a solution. Doesn't seem to be a problem, but we're going to see what that problem is in a second. Case 2 is when x is greater than or equal to negative 1. And we have positive expression for x plus 1 now. So when we take away the absolute value bars, we don't need to do anything. And this is a very easy equation to solve. We can just subtract x from both sides. Now, you can see part of the problem if you just plug these roots, these solutions back into the original equation. Let's plug 1 in first, because that's obviously the easier one. The left-hand side becomes the absolute value of 1 plus 1, which is 2. The right-hand side becomes 2 times 1, which is 2. So this is a perfectly valid root. The left-hand root that we got from case 1, negative 1/3. So negative 1/3 plus 1 is 2/3. the absolute value of 2/3 is 2/3. The right-hand side, though, is 2 times negative 1/3, which is negative 2/3. And that clearly can't be the case. We can't have the absolute value of anything equal to a negative. And so this is invalid. This is not an actual solution. So really, this is our only solution, x equal to 1. So what's going on here? Why do we get this value of negative 1/3? Let's take a look at the graph to understand this. So the expression on the left, y equals, well, the absolute value of x plus 1. We're going to graph y equals x plus 1. So that's a, hopefully by now, straightforward looking V shape with an x, the point of the V being at x equal to negative 1, the critical value. And then 2x passes through the origin and is a steeper line. And now it makes sense why we only get one point of intersection. So this point of intersection right here occurs when x is equal to 1 and y is equal to 2. So where's this point x equal to negative 1/3 on the graph? I like to refer to it as a phantom intersection. If you can imagine extending the line on the left, which remember is y equals negative x minus 1. If you extend it below the x-axis, you're going to get this point of intersection here, which has an x value of negative 1/3. But obviously that's a point on the line, y equals 2x, but it's not a point on the absolute value function, because everything obviously on the absolute value function is above the x-axis. So I like to refer to that as a sort of a phantom intersection, and you'll get it as a root when you solve it algebraically. So how do you catch it if you're not going to graph everything? How do you know it's an invalid root? Well, one way is to do exactly what I did, which is to plug the roots back in and actually see if they work or see if they lead to a problem. But we could have figured out there was a problem even before that. And to do that, we need to pay attention to the case statements. Because essentially what these case statements mean are that we're solving the equation below, but any solution we get is only valid if x is less than or equal to negative 1. Now the x value we got, negative 1/3, is not less than negative 1. And so immediately upon seeing that, we could reject it. Whereas when we look at case 2, this equation below is only valid for values of x greater than negative 1. And so then when we get a value of x equal to 1, without even plugging it in, we know that this is okay, because 1 is definitely greater than or equal to negative 1. Let's see another example, this time again involving quadratic. So absolute value of x squared minus 4 equal to x minus 4. What are the critical values? Critical values occur when x squared minus 4 is equal to 0. If you add 4 to both sides and then take the square root, don't forget about the plus or minus. So you have critical values at plus or minus 2. And again, it helps to have a sketch. And this time, let's take a look at this on Desmos. So absolute value of x squared minus 4 there's the absolute value of x squared minus 4. Let's turn this off for a second. So you can see it's the parabola coming down, and then at negative 2, instead of going down below the x-axis, it pops up above, and the vertex would have been 0, negative 4, but that gets reflected up and becomes 0, 4 there. And then again it starts coming back down again, and at an x value of 2, we're back to the original parabola. Now, what's the right-hand side of this equation? the right-hand side of this equation is x minus 4. So let's graph x minus 4, y equals x minus 4. And you can see we've got a problem. This line passes entirely below the absolute value function. We shouldn't get any solutions whatsoever. And so graphically, it's very quick, right? We look at the graph and we can say they don't intersect anywhere, and therefore I've got no solutions. But what's going to happen algebraically? It's important to realize what to look for if you're doing something algebraically. So we've got a quick sketch here of the function. This tells you where the critical values are at -2 and +2. So we have case 1 is when we have to reflect it when x squared minus 4 is negative, which occurs between -2 and +2. And if that's the case, when we take away the absolute value bars, we stick a negative sign in front of the expression. And -x squared plus 4 equals x minus 4. I can bring everything over to the right-hand side, and I get x squared plus x minus 8. That doesn't factor, so I'm going to have to use the quadratic formula. X equal to -1 plus or minus the square root of b squared minus 4ac. That's 1 minus -32, so that's 1 plus 32, which is 33, all over 2a. And if you don't think about the magnitude of that number, the sort of approximate value of that number, you may think, okay, that's fine, I've got 2 roots there. They're irrational, but so what? However, if we do a decimal approximation here, we see that one of these is approximately -3.4 and the other one is approximately 2.4. Neither of those roots are between -2 and +2. So again, what's going on there is that if you can imagine the parabola coming down below the x-axis and going back up, it intersects that line in 2 places. Well, these are the 2 x values of where it would intersect. So they are, again, what I call phantom intersections. So these are both invalid. You can ignore them both. In case 2, we have either x is less than or equal to -2, or x is greater than or equal to 2. And so that's when x squared minus 4 is positive, so we don't have to do anything when we take away the absolute value bars. This, again, is a quadratic. We can subtract x from both sides. We can add 4 to both sides, and it turns out it's a very easy quadratic to factor. And therefore x is equal to 0 or 1. Well, again, this is a problem. Certainly a lot easier. You could plug these back in, and you could see that the left-hand side becomes the absolute value of 0 minus 4, which is the absolute value of -4, which is +4. The right-hand side becomes -4. That's not true, so that's not a root. And +1, if you plug that in, you get absolute value of 1 minus 4, which is -3. And that becomes +3. The right-hand side is -3. So neither 0 nor 1 are roots. But again, if you just pay attention to the case statement, you can see that they can't possibly be roots either, because this whole equation is only valid for x values that are less than -2 or greater than 2, and 0 is not in that interval, neither is 1. And so these are both invalid as well. And so we've shown both graphically and algebraically that there are no solutions to this equation.